Hello, how are you? What is your name? Can you just pin down your name in the comment box so that I can let you know, so that I can know what's your name? So let me first introduce myself. My name is Dr. Saddam Leonardo Cap, and this video is basically the series of the several videos on the quantum mechanics. So I'm going to cover all the syllabus of quantum mechanics from the very basic beginning to advanced level. So today I'm going to discuss the fundamentals of quantum mechanics, and to that I first discuss the syllabus that what we are going to do cover in this whole series. Okay, so here is the syllabus that I'm going to specifically cover in this complete series. All right. So if you have any question specific to that, you can easily ask that. Okay, I have selected. Okay, you may have asked that why you have selected this kind of syllabus. Like I have selected this syllabus, but keeping in mind that you know people would do some research, right? Later on, maybe you do some research projects, or maybe you have some interest in PhD, or you have learned a little bit of quantum mechanics in your BSc from your institute or wherever you are. But the thing is that the thing that what happened with me when I was learning that why we are learning this. First of all, people like have given me a lot of experimental validation that okay, these are these experiments, they were not able to, Newtonian mechanics was not enough to actually give you the framework, give you the structure, why it happens, the prediction fails, and therefore people invented something very new in during 1930s and 1924, right? um, the thing is, it's good, but as a student, let us say you will ask that okay, how can we even, I have something, let us say that I want to invent something new, right? So the question that comes to our mind, today we have general relativity, right? We have quantum mechanics, we have quantum field theory. These are very well established theory. And if you follow any particular popular videos, you understand that today we have some problem with these frameworks, that GR and quantum mechanics cannot be unified, and hence GR has a separate game. On the other hand, quantum mechanics, quantum field theory has separate game. We cannot merge them together in a one picture, and this is one of the fundamental problem with this GR and quantum field theory. So if I look at back the history, we had Kepler, Galileo, and then come to Newton the genius, and then afterwards many researchers have came, and then after 200 years Einstein came, and he proposes something that invalidate the Newton's idea, and he recognized something and gave the completely new formulation of the universe, to understand the universe, right? So basically, if I want to become a great scientist, I must respect whatever has been done. All right. So let's say that GR quantum mechanics kind of theory is good, but it's failing. So you want to invent something new theory. Let us say some new SFT and so on, something new theory, right? That can merge GR and quantum mechanics as well as GR and quantum mechanics pretty well, right? But the thing is that, okay, how can I think of it? How can I think of this particular new theory? Well, whatever this new theory would be, it must respect whatever the success that these GR and quantum mechanics have, right? That's pretty fine. That okay, SFT in some particular limit must boil down to GR and quantum mechanics. And this is also GR happens. If you have put some kind of limit, then GR will automatically, become your classical mechanics, right? Classical mechanics is done by Newton mechanics. Similarly, quantum mechanics also give you the same equation of motion. In certain limit, it becomes classical, right? There is no problem to it. But the thing is that when quantum mechanics was not there, there was only classical mechanics. Then how Schrödinger actually thought about these quantum mechanics, or how the scientists at that time quantified that okay, this is the way, this is the approach in which if we can think, then we could construct a new class of theory, new class of model, new class of mechanism, right, to actually address something that is more fundamental, right? So in classical mechanics, we have a notion of position, we have notion of velocity, we have notion of momentum, and so on. And if you have any idea of quantum mechanics, you have a notion of position, but you have a notion of momentum, and these are not just your position, right? The position, they could be vector and so on, but in here we are acting as some kind of an operator in quantum mechanics. So the thing is that how we got this type of idea, what is the bridge between classical mechanics, quantum mechanics, so that I can understand the pattern, and similarly I will develop my understanding that okay, this is the true way to thinking if I need to become a very good theoretical phases. So that is my goal, and that is why there are, you can find many many lectures on YouTube, right? But I think there is a gap. People in YouTube, it is going to come and give you that, all right, this is the recipe, this is the question, all right, I have some course, I'm going to search it, I have the answer, and so on. All right, this is fine. In order to pass the exam, it is fine. But if you want to really do great, all right, and you want to delve deeper into something, right, then that is not going to help you. You have to increase your thinking, and that's why I'm making this video, to give you some new perspective. All right, that okay, this is the new perspective, and I must say that I will adopt some type of conventions, or let us say some type of definition, or some type of, let's say that, analogy that could be not, that is not going to be saying that okay, this is, you may be wrong, yeah, I may be wrong, all right, but the analogy I am going to give you, that can help you to understand, all right, this is the way we have to understand things. And maybe one day, if you are good enough, if you are a genius, then you can easily construct your new field theory, let us say new field theory, all right, that can encapsulate your GR, quantum mechanics, and whatever they have the limitations, all right. So with this in mind, let's begin our journey. And and i i follow, let's say that many, you can say that many lecture notes, all right, but the thing is that everything would be completely mine, and I want to restrict myself. Okay, these are the things that I have to discuss, but in a different way. I will try to convince you in a different way. Secondly, that each lecture would going to be like 1 hour, so it's like I am teaching you, I am giving you some kind of private tutoring, like, okay. So I'm going to ask you, I'm going to I'm going to take your questions, so I will always see your comment, and I will try to address it, maybe by making some particular video onto it, or I will answer to you on that particular comment. So don't forget to comment, and please pin down your name, all right, and what is your name, and what's your institute, and why do you, like quantum mechanics? Why? Because it's only just because that you have something in syllabus, and but I want to pass exam, and that's all. But you are very much curious to do some scientific contribution, and that is what we require, right? People can learn so many things, but the thing is that why I am making this video, because I like it. I like quantum mechanics very much, and since 5 to 7 years I was trying to make these videos, that okay, I will one day I will cover quantum mechanics. I have made some videos that is available in maybe in Hindi and so on. You may also check that out, but they are not good. So uh in this lecture series, I am going to cover everything from foundation to advancement of this quantum mechanics, all right, and I'm going to use my non-conventional method to make you understand, to make you feel that okay, this is the path that if I can think of, and that is how the development in some theory occurs, all right. So with this history, with this rich history, let us start our journey. First of all, let's what is the syllabus that I am going to cover in this whole series. So first, starting with the fundamentals. Fundamentals is that in one lecture, let us say in this lecture, or maybe the next lecture, I'm going to talk about the pure classical state. or classical physics. Basically, what is the meaning of classical, what is basically classical physics? That is post Newtonian mechanics that I'm going to consider. All right, then I'm going to talk about the history of quantum mechanics. That is basically depending on the experiments and so on, but not, I'm not going to go to that way. Something will be changed, but I think the syllabus will be like that. All right, then I'm going to talk about that, okay, what is basically the wave, right? You have already heard that there is a wave equations, and this wave equation is going to tell you everything about the quantum notions. So basically, what is wave, and how people have thought about that, okay, wave can handle this kind of scenarios. Thirdly, I'm going to talk about the quantum state. What is this quantum state, and how it is basically different from the classical state, and what are the things that is coming to, or you have to deal with it. All right, okay, any questions so far? Yeah, we will going to talk about so many things, like what are the notions, what are the operators, and so on. So there is no problem to it. uh Afterwards, I'm going to talk about the dynamics of quantum mechanics. Yes, the state that represents is that something, state is what, state is the physical property of any object, right? Let us say that you have a ball and you have thrown it with some speed. You have some object, you are trying to push it using some velocity. Then after some time, what will happen to its position, its velocity? What about its energy? What about its that where it would be, like location and so on, location, position, momentum, and so on, right? So these things are basically the entity, these entity called the state. So obviously the velocity depends on time, right? Anything which is not moving, after some time it is not going to move. So they are, it's basically the stationary. The dynamics is that how something is changing with the time. So if I have some quantum object, I can always associate some position, some momentum, maybe some velocity, some energy, right? So how these guys is going to change, and this is what we say, what is basically referred to as dynamics of quantum state. And hence it associates the energy, it's associated that, okay, what are the operators and what are the observations. In classical mechanics, we never think about the observation. Observation is what? Observation, yeah, we are the observer, right? If I have a lab, I am doing some experiment, observer, there is no problem because I am observing the experiment. But here you have to give some kind of name, that, okay, what are your observers? Observers means that the position, can you observe it? And although you can observe the position, do you have some kind of extent? At that extent only you can observe something, right? So we are going to talk about in detail, and that is what give a birth to uncertain principle. You have already studied in your class 11, class solid, class 12, maybe class 11th, right? The Pauli exclusion principle, the uncertainty principle, right? So all these things are, we are going to refresh over here, how these things arises and how the chemistry people are using those things. All right, okay. So continue to this. When we know how to deal with this, how to know the dynamics of equation, then we are going to understand that, okay, I have some kind of a box. Let's put an electron in this box, and what would be its dynamics? And that is very important. you know this is the most simplest equation. If I say that, what is the role of this, or what is the counterpart in the classical mechanics, is that you can be associate this thing as, let us say you have a particle of mass m and you have just given a velocity. All right, if you have just given a velocity, then what is its position? You can just simply say that, okay, position will be x is equal to vt. What is its momentum? Momentum is equal to m into v. Will it have any force? If the velocity is not changing, there is no force. So let's say that I have this any particle m, it has certain velocity, and there is no potential. Then what would be its state? How we are going to observe the x, observe the momentum, and so this is the most simplest thing that you can analyze with this kind of thing, right? So you can just remove that, okay, if I don't have any box, then what will happen, right? If I extend the box, then what will happen? All right, so this extension, how can we do this type of extension and so on, right? So there are a lot of things we are going to discuss from the basics. All right, Secondly, we are talking about the quantum harmonic oscillator. You have already realized that we have a spring and we can attach a mass to this spring, and a spring has constant k, and this is very popular, right? You have simple pendulum, it can oscillate, so you can have oscillator system. So similarly, over here we can have many oscillator system, because in one way or another we are, why we are studying quantum mechanics, because we want to know more about the crystals, more about the molecules. And you understand that in molecules there are bondings, right? Bonding by van der Waals forces and something like that. Okay, and these bonding, when the crystal forms, you have the particles and there are invisible bonding, and these invisible bonding can be thought as if that there is some kind of spring there. If some particle is bound with a spring, obviously there will be an oscillation. The most simple thing that I can think of, that okay, I have a quantum particle that is some way vibrating. In classical mechanics, this is the vibration that we are finding. In quantum mechanics, all right, there is a particle in some kind of potential. The potential is look like this one, and it has some minima. So if a particle given some kind of velocity, and if this particle comes in the minima, it will simply go here and here and there. So there is some kind of an oscillation going on. So if the some oscillation will take place, then how can we know its position, again, the energy, momentum, and all the observables I want to know, right? And there are more to it. There is called occupation state, that where it can live, right? Which is absent, like, okay, where it can go. If it is constant to move in x-axis, it's going to be obviously oscillating in x-axis. There is nothing. Over here we have something called energy state, that okay, this has, if this is the one, the particle is going to have this much energy, and so on and so forth, right? So these things we are going to eventually understand of what is the meaning of a state. Okay, here we have something have been done in the one particular axis, then we can say that okay, anything happens in two dimensions. So let's say that we have a two degrees of freedom, then what will happen? Then we have this rotation motion in classical mechanics. Something, a particle is attached with some particular x6, and therefore it can rotate, right? So it has degrees of freedom, but it has some restriction, because it cannot go here and there. Let us say I have just rigid, something is rigid, it cannot go over here, but it can move in some direction, right? Maybe circular motion, it has 2 degrees of freedom. With the circular motion, we know that there is some kind of an angular momentum, right? And there is a moment of inertia associated with this one. So basically the thing is important is the angular momentum. Objects can rotate, angular momentum is going to be conserved in classical mechanics. Now that angular momentum would become one of the observables, one of the operators, and that is very important. It becomes in quantum mechanics, because it is going to tell us more about the state of the particle, right? So angular momentum we are going to see, that is associated with the rotations, as we have already understood from the classical mechanics, right? And in later on we are going to relate it with what is happen if we have different type of momentum, that is called spin angular momentum, right? So we have just rotation angular momentum, and now we are going to introduce afterwards what is a spin. And afterwards, when we finish our angular momentum, I'm going to discuss about the hydrogen atom. Hydrogen atom is the most simplest atom, because in the nucleus, it has one single proton and single electron is moving around it. What would be the mechanics, right? How the energy levels will look like, what are the states that it has, like how it can occupy, and so on and so forth, right? We cannot discuss right now over helium atom. Maybe we are going to do atomic physics, then we are going to study more about the helium atom, maybe lithium atom, and so on. There are different ways we can handle without even doing a lot, solving the exact Schrödinger equation and so forth. And then we are going to proceed to more application. The first thing we are going to understand the electronic spin. Electronic spin have many things to introduce, that in electron they have additional degrees of freedom and so on. It's more with the electrons and how it is going to affect how we are going to understand the hydrogen atom spectrum and so on, hydrogen gas spectrum and so on. Similarly, we are going to understand the vector addition of angular momentum, something called the quantum particle can be categorized in terms of bosons, fermions, right? And these are the particles that we are have some interest that, okay, what is basically meaning? Can we distinguish between one electron to another electron, right? There are some other particles which is different from electron, and how they are going to different, and how we can classify them as a bosons or fermions, all right? And if some particle are fermions, they have some exclusion principle that they cannot occupy the same state, right? So we are going to discuss those things, and then we are going to discuss about live wires and dead stars. That, okay, we have understood a lot about quantum mechanics. Now can we understand something more astrophysical things, right? Or let's say that you have some gases, then what else it can get, how we can calculate the energy and so on. And afterwards, when we are finished with it, we are going to do the advanced quantum mechanics, that is that can we incorporate special theory of relativity in our case, right? There is a relativity, you know it, and relativity has to be merged with quantum mechanics, and then it becomes quantum relativistic mechanics. And later on, quantum relativistic mechanics has something, some kind of limitations, and therefore we have made quantum field theory. And this is actually important, because then we will understand quantum mechanics. There is no annihilation or creation of particle. The particle is there, but the thing is that how the particle is come to an existence. Only electron, proton, and neutron are the particles, or is there some or something more exist? This can be realized when only when we take into account relativity. So we are going to understand the framework of quantum relativistic mechanics by Paul Dirac. Dirac has given a lot of things. His contribution to quantum mechanics is insane, and he was kind of genius. So we are going to understand a lot about it, quantum relativistic mechanics. Then we are also going to understand, okay, the perturbations. All right, the perturbations are kind of very important. Why perturbations are important? Because in quantum mechanics, the solution that we will be having is of the differential equation. And this differential equation has order 2, means that we are going to talk about this d2, let us say psi over dx square. This is second order differential equation. In most cases, getting the solution of second order differential equation is not a trivial job. In quantum mechanics, you have to rely on so many mathematical tricks to actually get the solution of second order differential equation. And hence, for many cases, you can run out of these tricks. All right. Maybe in quantum harmonic oscillator, you can have exact solution. For hydrogen atom, you can have exact solution. Free particle, obviously, we have exact solution. But let us say I have something more. I have I have this quadratic potential, but I can make it a little bit flatter, right? How can I know this? How can I know the how will I find out the solution of this particular differential equation for this differential equation? Similarly, a electron is moving in an ellipse. It cannot leave the ellipse. How we can find the solution? Electron is moving on circle. It's simple. Electron moving on ellipse is kind of difficult. Electron is moving on a sphere, right? So in order to solve some non-trivial problems, we can approximate the solution, and this approximation is basically called the perturbations. And it's going to be very interesting to understand these perturbations. And when we are going to understand these perturbations later on, then we are going to understand the scattering problem. A scattering problem you have already heard of in quantum mechanics, that a person named Rutherford has done an experiment with his disciples, that take alpha beam and just bombard in the gold foil, and from there he discovered that there is some kind of nucleus in the side of atom living, right? And all the masses are basically concentrated on that particular nucleus. So scattering is going to become more important because when we are when we are talking about particle interaction, you see, you can see this board or anything because a light is colliding with the board, all right, and comes to your eyes. That is how, or simply it is emitting, that it is going to interact with your eyes, right? You are seeing the object because there is a light, and light is colliding with that particle and coming to your eyes. So there is interaction going on of the light with that particle. Now, the classical objects are very far greater than light, right? And we are not seeing any kind of disturbance. But if let's say that we are talking about electron has some kind of radius is 10 to the minus 18, diameter radius 18 meter, and now we are saying that okay, I'm going to throw it, I'm going to throw a light beam with an electron, then probably they have non-trivial interaction. So the light will go over here and it will bounce back. All right. And because of this bounce back, you are going to see how the electron is. So this bounce backing is called the scattering phenomena. And we have already seen a lot of scattering phenomena. Scattering is kind of phenomena which is all obviously there. There is no denying of it. How can we understand? And scattering is most important to probe the quantum mechanical structure. You want to x-ray it, you are giving x-ray to any molecules, and you came to understand that okay, fine, what is the structure of that crystal, of that molecule, and so on and so forth, right? And you will study it in solid state physics. So here, quantum mechanically, how can we deal with this scattering? And for that we need to have understanding of classical mechanics, because in classical mechanics we have the reference frame, that okay, where is our frame? One frame can be in the conservation of momentum frame or something like that, okay, center of mass frame, sorry, center of mass frame, or some non-center of mass frame, all right, some laboratory frame. Same thing we are going to do over here, right? But scattering problems are kind of very hard, very difficult to actually comprehend, and therefore we require the perturbations. And perturbation means that we are going to find approximate solution of the known solution, right? Of the complex system. So how those things can actually those methods can be applied over here to understand those kind of things. So are you understanding the point? So, in nutshell, what we can say that we are in this lecture series, we are going to understand a lot. So, my idea is that, therefore, I have constructed the lectures in 1 hour video, right? Because if I'm not making 1 hour video, then you are going to lose the essence, and therefore I don't want to make my channel fill with like 300 videos. So maybe in I will try to probably hit only 40 videos, and in 40 videos that is 40 hours, and in 40 hours we are going to cover, I will try to cover all these things. In one lecture I'm going to cover this classical state. In second lecture I'm going to cover the question with related with the history of quantum mechanics, quantum origins, but I'm not going to go very fast. The pace would be like the simple pace, right? And what I am going to skip, that I will maybe skip some deep derivation, although I am going to give you I will try to give you everything. But if I see that okay, some derivation are very very not hard but very lengthy, then I'm going to skip some of the part, and I will land on those important features, that okay, fine, this is the solution and you can look for it. Or maybe I will make some 1 or 2 videos explaining that how to do those particular calculations. But the more interest would be to actually understanding those calculations, as well as the results that we are going to obtain from there, right? I will also try to, show how we can use Mathematica. All right. Now, why I'm going to use Mathematica? Because in your conventional maybe classes, people will only teach you about theoretical way, mathematical way to get these solutions. But here I'm going to say that, okay, you have maybe a good computer and maybe you can install any mathematical version, or you may also, if you know Python, you can easily write some code to Python. I will also let you know how to write the code on Python. And some quantum mechanical problems we are going to actually see from mathematica, that okay, I have this one, I can easily find the solutions, and then there is no problem, then we can easily discuss the solutions, that okay, how things will look like. Now this is very much important because we are entering in the age of artificial intelligence, and if you have computer, then I think why to waste too much time on understanding or doing the calculations, although it is very good. If you really want to become a genius or something like that, right, you have to understand that how the mathematics work. But it's for fun. I'm saying it's for fun, that okay, I know how to solve the Bessel's equation or something crazy idea, because when there was no computer, people have actually came up with a real and interesting ideas to solve, which looked unsolvable, right? So if you understand that mechanism, that oh my god, I can implement those ideas, then it will actually push you in, it will give you the freedom of independence. What is the meaning of it? Freedom of independence, that the same thing. The thing is that it will give you the confidence. It will give you that, okay, I have learned now some pattern, that okay, this could be the idea that I might, it may help in some of my other problems, right? That's why we should not skip those mathematical part. We should learn as much as mathematics we can. If you are doing physics, you should be very good in mathematics, right? I'm saying that why you have to good in mathematics, because eventually I will let you know when I will be explaining the classical thing. I will try to give you, my approach will be more mathematical, because if you want to theorize something, you want to theoretically give your you want to make a theoretical model, so you require mathematics, obviously, yes. But uh, just like your argument, right? Let us say that you have some argument, considering an example that okay, somebody is there who wake up at 6 a.m. and reach to school, and for reaching he took or she took some bus, and then go to some one place, and then he again took some other bus. So can you just to model it to predict actually that at what time this person will actually reach to school, right? Now, this mathematical modeling is important, because now you have just given you, somebody has given you some arguments or some path. This has been done. Now, can you mathematically do the job? Because mathematically is where all the statements have some logical construction, right? You cannot simply skip. If 1 plus 1 is equal to 2, then you have a great proof for 1 plus 1 is equal to 2, right? You cannot simply skip it. So if something is universally acceptable, that okay, this is happen, so nobody will gonna just take your English. It should be supported by some mathematical argument, that okay, this is how we can do it, right? So eventually we want some language in which we can speak, and we want to translate our English into some mathematical world, right? And the translation is only can happen if we know, if we have constructed some differential equation. And differential equation is everywhere, right? Differential equation basically tell you the dynamics. So no matter where you no matter what is your theory, differential equation would be there. So understanding how to solve this differential equation is going to be vital, right? If you do your research and so on, making your own theory, differential equation is going to come everywhere. So my um, I want to ask something from you, that you should purchase some mathematical physics book. If you have, you can also download from internet, and brush up your mathematical physics, right? if you know, but if you brush up your mathematical phase, it's going to be very important, particularly the partial differential equations, and let's say that at solving the differential equations of higher order, right? Higher order, particularly the second order differential equation. So these are going to be, come up very often in quantum mechanics series, right? So although I am asking to, a lot, but you don't have to, do so much, because I'm going to do everything in this series, and you are going to see that how amazing it will be to sit in the lecture, listen to the lecture, and go through it, and bring your book, note down it, and if you have any question, just pin down the comment, and I will try to answer in the next video. So this is Saddam Cap signing out. We keep it here, and see you in my another video. Please subscribe and share it to your friends. Thank you very much.